Okay, I think we'll get started. If you're coming from the GNL project, I encourage you to look at the introductory videos for this course to make sure it's the right one for you. Today we're going to talk about kinetic and potential energy. So last time we talked about energy, kind of introduced the idea, did talk about how it has this conservation property. There's two types, kinetic and potential, and as we can convert one into the other so that the total amount of energy is conserved. And we're going to talk specifically about conservation of energy next time. But let's kind of work our way there. Okay, so we have kinetic energy as 1/2 mv squared. There's always this rotational analog, so we've seen that all the way along throughout the course now. And so I'm just going to bring these along for the ride. So what's our analog here for mass? It's moment of inertia, and then angular velocity instead of linear velocity. We have a relation to momentum. So we know that momentum is mv. So if we solve for v, we get p over m, and then we can stick p over m in for v here, and we get 1/2 m p squared over m squared. One of the m's will cancel, and we'll get k equals p squared over 2m, which is an important relationship between energy and momentum. The rotational analog would be L squared over 2I. Okay, here's some formula for potential energy. Potential energy in gravitational field is mgh, and for a spring, it's 1/2. This is 1/2 k delta x squared. Now you might be, if you're remembering from last time, you might be thinking, well, don't we have to only talk about energy as a difference? And that's absolutely true. These formulas are kind of hiding the reference zero. So this is mgh, where h is the height that you are at relative to your 0 point. So if I'm in this room, I might say the height of this relative to the floor. But if I'm maybe I'm really interested in the height of this relative to the center of the Earth. So this height is always relative to what you defined as your 0. So we'll be more careful in the problem that we're going to work to use a delta U, but this is the formula we'll see. Likewise with the spring, this is a little more obvious. This delta x is, so really this is a delta U compared to the stretched position. So this is the displacement from equilibrium squared. That would give us our energy versus if we're sitting at no stretch in the spring. Okay, well, let's see how this can work and this interrelationship, and again, hinting at here now this conservation of energy. Let's go back to a problem that was fairly difficult for us at the beginning, and that's this leap problem. So we're going to jump into the air, and once we leave here until we land here, there's nothing we can do about it physiologically or athletically. It is simply the physics of us flying through the air. So let's imagine we leap to a height of 1/2 meter, and we want to know what was the launch velocity. So that was one of the questions we were interested in. So let's do it this way. So we're going to reach this height. So let's calculate a delta U. That's going to be the final position of height h minus the initial position of 0. So the floor is 0 here. So our delta U is going to be mgh. Now, let's think about our kinetic energy. Right when we leave, we have a launch velocity, and then when we get to the apex of our jump, our kinetic energy is 0. So final velocity is 0, our final speed is 0, and then we have our launch velocity here. Now, we know that as we jump, we're going to slow down, we're going to lose kinetic energy, but we're going to gain potential energy. So there's this inverse relationship because of conservation of energy. So delta U is minus delta K. And so let's do mgh equals 1/2 v launch. The minus signs have taken care of themselves here. Now we see that the m's cancel. So this was something we thought was kind of interesting right at the beginning there, where we were doing these leap problems, is that it doesn't matter, the size of the athlete. As long as the launch velocity is what it is, it will reach a particular height, regardless of the weight of the athlete. And we can see that happening here. The weights cancel, and then we calculate a formula for launch velocity, which we've used before. And for this particular problem, we can plug in our numbers and we get a launch velocity of 3.1 meters per second. Okay, now we talked about work last time, and I mentioned that there's this, that's another way to categorize. So we have kinetic energy, potential energy, and then we have work and heat, as I mentioned, or thermal energy. So let's talk a little bit about thermal energy, also known as heat. And this is due to friction. So anytime we have a lossy system, so where we're rubbing the box across the floor, that energy is going into the floor. It goes into heating up the interface there. And so we have a thermal energy associated with friction, and we have a thermal energy associated with drag. So let's go back to this problem that we worked on last time where we were bringing this box up this ramp and it was frictionless. So we showed that the work going up the ramp is the same as the work lifting the box from the ramp. Well, now let's add some friction. So if we were to take this box and lift it from here to here, the work done there would be mgy. Right? But now we're going to slide the box up, but the box has some friction. So the work we're going to need to do is develop any change in kinetic energy. So are we speeding the box up? Well, no, because we're at a stops. We're stopped here. We're going to slide it up. So we certainly did speed up the box, but we're also slowing the box down. So we look at just the endpoints. Here, v equals 0, and here, v equals 0. Right? We just slid it up to the top of the ramp. So the change in kinetic energy is going to be 0. Now, if we were running it up and it's going to jump off the ramp and we wanted to see what was the work done to get to the top of the ramp, we would have to include that extra velocity there in the work needed. Then the change in the potential energy is just energy due to position. So that position is at height y, so that's going to be mgy, which is exactly equal to this work here. But we have this extra bit, the frictional piece, and so we have the friction bit sliding along the hypotenuse. So notice this is h and this is y. Okay, so kinetic energy, or kinetic and potential energy, their sort of teeter-totter relationship here due to conservation of energy is a really important way to solve problems. And then we have systems where there's no loss to the environment. Those are called conservative systems. Then work and the change in potential energy are going to be equal. But in systems where there is interaction with the environment, for example, friction and drag systems, then the work will not be equal to the change in potential energy because we get some loss due to the heating of the surface in the case of friction, or heating to the air in the surface of drag, and that consumes some of the energy needed to perform the work.